Here we have another question to deal with from AP Mechanics. Let's try to take a look at the question. A large circular disk of mass m and radius r is initially stationary on a horizontal icy surface. A person of mass m by 2 stands on the edge of the disk. Without slipping on the disk, the person throws a large stone of mass m by 20 horizontally at initial speed v0 from a height h above the ice in a radial direction, as shown in the figures above. The coefficient of friction between the disk and the ice is mu. All the velocities are measured relative to the ground. The time it takes to throw the stone is negligible. Express all algebraic answers in terms of mass m, radius r, velocity v0, height h, coefficient of friction mu, and the fundamental constants if and where appropriate and necessary. Let's try to answer this question. Derive an expression for length of time it will take for the stone to strike the ice. Since there is gravity involved, the stone which is projected horizontally will obviously undergo projectile motion. And since it undergoes projectile motion, we will use the necessary equations under projectile motion. So under projectile motion, the vertical height y, which is h in this case, can be found out by the formula I minus y naught is equal to the vertical component of velocity, initial vertical component of velocity vy into t plus or minus half gt square. Here, since the body is going down, we are going to use plus because it is in the direction of gravity, not against, half g t square. Here y minus y naught is the height h. Here, since it is thrown horizontally, the angle of projection theta is 0. I'm sorry, let me write 0. Since Vy is nothing but V into sine of theta, the initial vertical component of velocity is going to be 0 as it is thrown horizontally. Height h is equal to 0 into t plus half g t square. When I rewrite the formula in terms of t, I get t is equal to 2 times h divided by g whole under a square root. So this is the expression for length of time taken for the stone to strike the ice. This is assuming that there is no air resistance. Move on to the next part of the question. Assuming that the disk is free to slide on ice, derive an expression for the speed of the disk and the person immediately after the stone is thrown. Here, since there is no external force involved, we are going to use the conservation of momentum. Conservation of momentum is a very simple concept. It says that the total momentum P initial, that is before collision, is equal to the total momentum P after collision, which is final PF. Since initially all the bodies, that is the disk, the person, and the stone, all of them are at rest, the total initial momentum is considered 0, while after momentum, we consider the disk and the person as one single entity, whereas the stone is considered as another entity. The momentum of the stone is already given. Since momentum P is nothing but mass times velocity, momentum of the stone can be considered as mass of the stone, which is m by 20 into its velocity. Its velocity is towards the right, which is assumed as positive. So plus v naught plus the stone is one separate entity, while the disk and the person are considered as two separate entities or two combined entities, sorry. So since the stone is of mass m, the person of m by 2, the total mass is m plus m by 2 times its velocity v, which we are going to find an expression for. I can rewrite the equation as minus m into v naught divided by 20 is equal to m plus m by 2 gives us 3m over 2 into v. Mass m gets cancelled. 2 simplifies the 20 on the other side. So this gives us value of v as a negative v naught divided by 30. This is the correct value or the correct expression which gives us the velocity of the combined masses of the disk and the person after throwing the stone towards the right. The last part is derive an expression for the time it will take for the disk to stop sliding. So as the disk slides, we know that it does work against friction. It does work against friction, and friction is nothing but frictional force F, let's call it, is nothing but mu into normal. Since here the weight W acts downwards, normal acts upwards, and there is no acceleration, resultant acceleration vertically. I know that the normal or the reaction force is nothing but the weight. The frictional force is mu into m into g. Now, we are asked to find out, derive an expression for the time it will take the disk to stop sliding. The disk will stop sliding exactly when the work done against friction is equivalent to the force applied by the friction times its acceleration. So since work done is force into displacement, the work done against friction is equal to the frictional force mu mg into A. Here we can find out the work done against friction as the work done against friction is nothing but what causes the resultant acceleration. So the equation given before was W equals F into D, where we substituted F as the frictional force mu into M into G. Hence, since it is impossible for us to find the displacement and work done both in the same formula, we are going to use another formula instead. That is resultant force sigma F, which is equal to MA, is nothing but the frictional force FF. We have already found out frictional force as this. So when we equate MA as mu into M into G, I get A is equal to mu times G. Since we know the acceleration, and I also know that the final velocity is going to be 0 when it comes to a state of rest, I can use the equation of motion. V is equal to U plus A into T. Here, I always need to find out the time it takes for it to stop sliding, which is T. Rewriting the equation in terms of T, I get T is equal to V minus U divided by A. Here V is 0. U is substituted from the previous expression as in the previous expression for answer B. We found out that V is negative V naught over 30. So we are going to substitute this as the value of U. That is negative V naught over 30. And we are going to divide this by A, which is mu into G. So time T will become equal to V naught divided by 30 into mu into G. This is the final expression for time taken. The mistake we committed earlier is assuming or trying to find out the work done and then using that to find out the time taken. Instead, we are going to use the resultant force formula to get the answer in a much simpler and a faster method. Thank you.